Hello there, wonderful people. In the last video, I explored the fact that a complex number z can be expressed very generally as r times e to the I phi, and that it turned out that this representation by Euler's formula was equal to the polar representation of that same complex number, r times cosine phi, plus I sine phi, right? And so this equality here was by Euler's formula. And so what we can see here is that this form here on the left is basically a really elegant, nice package to express our complex number in terms of its polar coordinates r and phi. So now let's go ahead and use this fact for like some practical physics. And in fact, what we're going to do is we're going to use Euler's formula to help us solve a differential equation, the simple harmonic oscillator differential equation. So let me go ahead and draw a wall here, just like this. And let me go ahead and put in a little table, right? And this table is completely frictionless, okay? And so what we have is I'm going to put a little spring on this wall, this little squiggly line, that's my spring right there, okay? And at the end of the spring, I have a little box, a little cube. This cube has some mass m, and I'm going to put its center of mass just in the center of the cube, just like this, okay? In this picture, I haven't stretched out or compressed the spring at all, so this spring is currently in its equilibrium position, right? Which again, that means that I haven't stretched or compressed the spring at all. So let's go ahead and identify the location of this cube's center of mass. Again, the significance of the center of mass point is that we have chosen, right? We're just going to identify the position of my cube in its entirety just by looking at this one point, the center of mass. So that's going to be the point that we trace. So I'm going to go ahead and put a little x-axis on the table, right, in blue here. And we understand that we only need one coordinate to represent the position of this cube because it's constrained to just basically oscillate, once I ultimately pull the spring and let it go, it's going to oscillate back and forth on this frictionless table here, right? So I only need to pick out its location in the x direction. Okay? So this location here, this is the equilibrium position x naught. And in fact, because it's convenient, I'm going to define x naught to be the origin of my coordinate system x. So this is my 0 point, basically. Next, let's go ahead and imagine that we actually stretch out the spring. And so all that I've done here is I've taken my spring and I've stretched it out so that instead of my cube being at x equals 0, of course, now it's at some position x. Now, for convention, let's go ahead and we choose to define our positive direction to the right, and we choose to define our negative direction to the left. Okay? We always need to make sure that we define, right? We define what our directions are in any coordinate system. And if we wanted to be extra rigorous, we could call this the positive, like, I hat direction, and we could call this the negative I hat direction, where I hat is a unit vector. But we don't have to be too rigorous, because again, this is just simply a 1D problem. This is not that complicated. And so I'm going to define this spring as a Hooke's law spring, right? In every physics situation, we're trying to model nature, right? We're trying to come up with a model of nature. So in the Hooke's law model, so this is Hooke's law, if I displace my cube on this spring, and really it has some displacement delta x, I've stretched out the spring some delta x, but because my initial position is 0, this is just, of course, x. Like I said, we defined our equilibrium position very conveniently. The point is, the force on my spring is just going to, or the force from my spring on this cube is equal to some proportionality constant k, right, times the position of my cube, x. So let me just clarify real quick the goal of this problem, right? I want to set up an equation of motion with Newton's second law, F equals ma, and then we're simply going to use this equation of motion. We're going to solve this differential equation so that I can find the exact position of my cube at any given moment in time t. So I want to get the position of my cube x as a function of time t. Sound good? And so of course our objective here is to write out Newton's second law, F equals ma. So F equals the mass of my cube m times the acceleration of the cube, right? In the x direction, of course. And this is simply equal to the spring force, right? And remember, I gave the spring a positive displacement, and I had a negative spring force in response to that. So this is going to be equal to minus kx. Right, and we would get the same relation if I had chosen to compress the spring instead of stretch out the spring, which is I would compress the spring, which would involve a negative x, or a negative displacement, right? And then I would get out of that a positive force because the compressed spring would now push the spring out instead of pull the spring back in. So I'd still get that opposite sign relationship. But for me personally, I like to just conventionally always define my displacements out in the positive direction so that, oh, yeah, I can see that I get a negative force. Okay, the force equals negative kx. It's just really nice to do it that way for me. But you can get the exact same result if you choose to compress the spring instead of, uh, expand the spring. But let's go ahead and now rearrange what we have here, right? So we have, I'm just going to rearrange this equation right here. And so we have d squared x dt squared plus k over mx, and this equals 0. And now, very quickly, just take my word for this. It's useful to define a quantity omega squared. We're going to define omega squared as k over m. And so again, we can write out this equation as d squared x dt squared plus omega squared x equals 0. And this right here is the differential equation for a simple harmonic oscillator, right? That's what this abbreviation is. Simple harmonic oscillator. And so this is the first real differential equation that I'm going to explore really in depth on this channel. And so we're going to look at this very carefully. We're going to look at it very carefully, and we're going to learn a lot about the properties of differential equations and how differential equations work by exploring this problem. Right, and so I've gone ahead and just written out our differential equation again here, and in the top left I'm reminding us that our objective, yep, we just want to find x as a function of t, very simply. I want to find the position of the cube if you give me any time t. Great. So in order to actually solve this differential equation, we first have to analyze it very carefully and identify a few key aspects of it. some properties that are going to help us solve this differential equation. So the first key aspect that we're looking for, we have to identify that this is a linear ODE. ODE, by the way, means ordinary differential equation. That's all that means. So I'm going to say ODE quite a bit, but that's all that it means. It just means ordinary differential equation. An ODE is linear if it has the following form. A1 of t times x of t plus A2 of t times dx dt plus A3 of t d squared x dt squared. And we can continue this pattern out, dot, 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 for a sub n of t times the nth derivative of x with respect to t. And this all equals a0 of t. Right? And just so we're totally clear, each of these little a1, a2, a3, these are just functions of time. And then we're taking these and we're multiplying them by first x, then the first derivative of x, then the second derivative of x, and then we keep going to some nth derivative of x. We're adding up all these terms, and this equals, again, some other function of t, a naught of t. This is the form of a linear ordinary differential equation. Okay? So first off, let's go ahead and verify that this equation here matches this form. That's the first thing we're going to do. And the second thing is I want to convince you that, and I'll do this next, I want to convince you that this form here is appropriately called a linear ODE, okay? Like I want to explain why this is the form of a linear ODE at a certain level, okay? Right, and so of course we can see that, yeah, this equation up here has this form. It's just a very specific form where A3 is equal to just 1, right? And where A1 is equal to omega squared. And then all my other terms are 0, including A naught, right? So we just have a very specific form where A1 is equal to 1, or sorry, A1 is equal to omega squared, A3 is equal to 1, and this sum equals 0. Okay, so we feel good that, that these forms match. Now let me go ahead and see if I can convince you of, exactly, maybe a slightly nicer way of describing a linear ODE. Okay? So one thing I can do is I can describe or define a differential operator, d hat. And what it's defined as is a1 of t plus a2 of t times d dt plus a3 of t d squared dt squared dot 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 dot, and it goes all the way up to an of t d to the nth dt to the nth. If I choose to define my differential operator in this way, we can see that this equation up here reduces down almost immediately into a very, very nice form, where I take my differential operator d hat, and I operate it on x of t, and this is just going to equal a naught of t. Look how nice that is, right? I just take my differential operator, operate it on x, and it gives me a naught of t. So now let's go ahead and get to the main point, that if my operator d hat has this form up here, okay? If it satisfies the following two properties, which I've listed down here, then it's a linear operator, okay? If I take d and operate it on alpha x, then this simply equals alpha dx. And if I take d and operate it on x1 plus x2, then this simply equals dx1 plus dx2. Because my differential operator in this form does in fact satisfy those two properties, please verify it for yourself. All you have to do is take this differential operator and then distribute it out over the alpha x and just show this equivalency. It's really not that bad. And then do the same thing and instead operate it on two functions x1 and x2, right, added together and show this property. Take 5 minutes and do that. I'm not just for the sake of time. But because these two properties are satisfied, we have 100% confirmed. So 100% confirmed. Ugh, I can't write. There we go. We have 100% confirmed d hat is a linear operator. And as such, our function d hat, or any equation that can be written in the form d hat of x equals a naught of t, is linear. Hopefully we feel 100% fantastically clear about that. And so with this notion of a differential operator, we can see it's really easy to tell when something is or isn't a linear ODE. For example, this quick example here, right? We can see immediately that this is a nonlinear ODE because there's no way I'm ever going to be able to define a d hat just in terms of functions of t, right? Functions of t times, nth derivatives with respect to, nth derivatives with respect to t. I'm never going to be able to write out this function here as d hat operating on x, right? It's not going to happen. I have d squared x dt squared times d cubed x dt cubed, and I have x plus 3 squared dx dt. It's impossible, right? So this is definitely a good area to practice to make sure that we can write out linear ODEs in the form of d hat x, and that we can observe that it's impossible to write out nonlinear ODEs in terms of d hat x, where again d hat has this definition right here. And so now I've went ahead and I modified our first kind of property up here. Look how nice and simple it is now that we have this notion of a differential operator down. And so let me ask you, can you come up with a differential operator d hat such that when I apply it to x, it satisfies this relation? And hopefully now we're looking at this, we're going, yeah, that's easy. Look, I can take a d hat, I can just define it as d squared dt squared plus omega squared, where omega squared is just a constant. And of course, if I apply d hat onto x, I take d hat and apply it onto x, that's just going to equal this, d squared x dt squared plus omega squared x. Beautiful. And so we have this form here, right? This is a linear ODE. Now, specifically, we can see here that we have d hat x. It equals a naught of t, and specifically, this a naught of t is equal to 0, right? D hat x is equal to 0, right? because of that, we can come up with a second key property of this equation. This equation is a homogeneous ODE. That's the second property it has. And it has that property because A naught of t equals 0, aka d hat x equals 0. Okay? If A naught of t is non-zero, then we would call this a non-homogeneous ODE. We have one more property we can identify. This is also a second order ODE. Why do we call this a second order ODE? Well, that's very simple. Because the order of the highest derivative in this equation is 2. Therefore, it's a second order ODE. That's about it. It's pretty simple. So, has a highest derivative of d squared x dt squared. And so it's a second order ODE. So to kind of summarize all of these three properties in English, we have that our ODE here, it's a linear, homogeneous, second order differential equation. Those are all key descriptors of this equation. So repeat that to yourself, get the language down, and make sure that you feel comfortable describing this as a linear, homogeneous, second order differential equation. Now that we've identified these properties, it's going to make it 10 times easier to solve this problem, to solve this diff-EQ. So that's our next step. Let's go ahead and solve this differential equation. So in order to actually solve this differential equation, we're going to use a technique called an Ansatz. And an Ansatz is a German word, and basically what it means is that we're going to make an educated guess or a proposal for the solution which we will verify. So if I were to look at this equation, d squared x dt squared plus omega squared x equals 0, I wonder, can we propose a very kind of general form of a solution that could potentially satisfy this, right? So I need a function, x, that when I take its second derivative, outputs something that has the same form of x, some scalar difference, right? Probably the opposite sign, right? Because it needs to cancel out with omega squared times x, right? But somehow when I take the second derivative, I need a function that still looks exactly like x in order for, this and this to actually cancel out with each other. Can we think of a function that kind of does that? When we take derivatives of it, it looks similar to our original function? I can think of one function, right? X as a function of t equals e to the alpha t, right? If I take derivatives of that, that's going to give me e to the alpha t times, a constant. And that looks promising, right? Because if I plug that in for x2, it's also going to give me e to the alpha t. And maybe I could get those e to the alpha t's to cancel out with each other for some value of alpha, right? So this is a very common ansatz, e to the alpha t. So, but even if you don't buy the intuition that I'm saying at this moment, let's just go ahead and lock this in. I'm going to say this is my educated guess. I am proposing that this ansatz, if I have a x as a function of time in this form, it will solve my differential equation for some alpha. That's my claim. Okay? So, ansatz. X as a function of t has form e to the alpha t. And now all we have to do is let's verify my ansatz. And of course we can do this just by plugging in x into the differential equation. So if we have d squared x dt squared plus omega squared x equals 0, let's go ahead and plug my ansatz in. Then I get d squared e to the alpha t with respect to t squared plus omega squared e to the alpha t. This is 0. We can very easily take derivatives of e to the alpha t with respect to t. This is simply equal to alpha squared e to the alpha t plus omega squared e to the alpha t equals 0. Wow, would you look at that? I can cancel out these e to the alpha t's. Beautiful. So therefore, alpha squared equals minus omega squared, and alpha equals plus or minus the square root of minus omega squared. Ooh, square root of a negative number. Whoa. Okay. We're okay with this. This will give us plus or minus omega times I. Okay, so I mean, I think there's two pretty noteworthy things to note here. The first thing is that alpha has two solutions, right? And the second thing of note is that both of these solutions are complex in nature, which is bizarre maybe at first. So the first thing is, right, let's address the two solutions. That this implies that really this differential equation here, our differential equation, it almost had like two solutions. Where x1 of t is equal to e to the I omega. Oh, don't forget the t. That's important. And x2 as a function of t is equal to e to the minus I omega t. Now get ready, because there's going to be a lot of information in this next statement, and we're going to break it down, okay? So right now I have two solutions, x1 and x2. Here's my claim. First off, x1 of t and x2 of t are what we call linearly independent solutions. So there's the first part of my claim. And thus, I can write my total solution x of t as C1 x1 of t plus C2 times x2 of t, where C1 and C2 are arbitrary constants. Okay, that's a lot of information to break down. I mean, I'm making a lot of claims here. So let's go ahead and just go through one at a time, right? x1 of t and x2 of t are linearly independent solutions. Okay, what's it mean for functions, right? We have functions of time. What does it mean to be linearly independent? So let's go ahead and start there. So let's go ahead and start by discussing linear independence. And by the way, these words that I'm using, like linear independence and linear operator and things like that, like they have much more general kind of meanings in the context of linear algebra and abstract linear algebra, etc. But I don't want to get too general because I think that that would be confusing. So I'm just discussing these ideas in the context of this differential equation. But if it kind of feels like we're discussing, like linear algebra type ideas, um, if you have any experience with linear algebra, yeah, that is basically the idea here. So just like in linear algebra, linear independence tells us that for some scalars, for scalars alpha and beta, if alpha times x1 of t plus beta times times x2 of t equals 0 for only for only uh, alpha and beta equal to 0, then x1 of t and x2 of t are linearly independent. But go ahead and verify. Let's verify that, first off, my solutions, e to the I omega t plus e to the minus I omega t, are linearly independent solutions. Let's do that real quick. So I have some alpha times e to the I omega t plus beta times e to the minus I omega t equals 0. Can you come up with some constants, alpha and beta, such that basically this term and this term cancel out to equal 0? I sure can't. And if you need anything more rigorous, right, we can take out an e to the I omega t times alpha plus beta times e. This is now to the to the minus 2I omega t. And yeah, we're never going to have just a constant alpha that always cancels out something that is a function of t. It's not going to happen. You can't generally define a constant to cancel out with a function for all t, right? Unless that function in itself is just a constant as well. Um, but clearly here it's not. So the point is that e to the I omega t and e to the minus I omega t are linearly independent solutions. So hopefully we'll feel awesome about that. So we've confirmed that these are linearly independent solutions. So I'm going to erase this and we're going to go down and we're going to analyze the second part of this claim. Because x1 and x2 are linearly independent solutions, I can write a total solution, x of t, as c1 times x1 of t plus c2 times x2 of t, where c1 and c2 are arbitrary constants. So remember when I was talking about the differential operator, right? And that the differential operator is a linear operator? That's going to make this second fact here really easy to prove, okay? Because, remember, if we had our differential equation, d squared x dt squared plus omega squared x equals 0, I could write this as d hat x equal to 0, where d hat was defined as d squared dt squared plus omega squared. Remember all of that? What happens if I plug in this proposed total solution in for x? Let's find out. So I have d hat of c1 times x1 of t plus c2 times x2 of t equals 0. Let's see if I can find some properties of linearity that are going to help us break this down. And so let's go ahead and use those linearity properties, right? So first, one, we're going to use the fact that if I take a linear operator operated on two functions, f1 plus f2, because this is linear, this is equal to a hat acting on f1 plus a hat acting on f2, right? That's the first property we're going to use. So that allows us to rewrite this up here as d hat times c1 times x1 of t plus d hat times c2 x2 of t. And now let's go ahead and use our second property, 2, that a linear operator a hat acting on some scalar multiplier times some function f is going to give us alpha times a hat acting on f, right? And this is what lets us pull these arbitrary constants, c1 and c2, outside of our operators. c1 d hat of x1 plus c2 d hat of x2 of t. Awesome. This is a really powerful fact, right? That we can rewrite d hat with this entire function inside, and we can break it apart because d hat is linear in this way. Why is that powerful? Well, we already proved that when I apply the derivative operator d squared dt squared plus omega squared, I already proved that when I apply that to x1, right, I already proved that d hat acting on x1 of t would give me 0. And I already proved that d hat acting on x2 would also equal 0, right? That's what we did all of this work for, right? To find the alphas such that when I plug this solution into my differential equation, it would output 0. So what do you know? If d hat times x1, or sorry, if d hat operating on x1 is 0, and d hat operating on x2 equals 0, we get c1 times 0 plus c2 times 0. Wait, this still all equals 0. In other words, we just proved, right, because the right-hand side of our differential equation is 0, and we get 0, is equal to 0, right? These are identical, of course. We just proved that our total solution x can be written as c1 times x1 of t plus c2 times x2 of t, right? We did all that effort to prove that. And the reason why is because when you take the differential operator on x1 and you take the differential operator on x2, both of these still output 0, and 0 plus 0 equals 0 at the end of the day. That's why we're able to combine our linearly independent solutions, x1 and x2 together, to get one total final uh, uh, solution to this differential equation. This is a very important fact. The fact that we can add solutions. So this fact that we can add linearly independent solutions together and again, I'm going to emphasize that this is for linear differential equations. This is known as superposition. This is the principle of superposition, that if I find multiple solutions for some differential equation, I can take those solutions, add them together, and get a total solution that satisfies the same differential equation. And let me make one more remark. Remember that our simple harmonic oscillator equation, this was a second order ODE. Remember when we made that categorization, right? Because the highest derivative was the second derivative, right? This is second order, and we have two linearly independent solutions. It turns out that this is not a coincidence, right? And I'm not going to spend even more time proving this fact, although it can be done. I don't want to spend more time than I've already spent on this video here. It's getting pretty lengthy, but this is a really important kind of fact to know, right? We should just have this down. If I have an nth order, an nth order let me put the emphasis on this, linear differential equation, it will have n linearly independent solutions. This is a very general fact. So if I have a fourth order differential equation that's linear, it will have 4 linearly independent solutions. And again, we can get the total solution by writing this is called a linear combination of your solutions, right? So I could write out C1 times X1 plus C2 times X2 plus C3 times X3 plus C4 times X4, and this would satisfy that fourth order differential equation, right? So this is a very, very important fact, And basically now, because I never pointed this out at the beginning, but for any differential equations going forward, now we know, okay, I've got a third order differential equation. I'm looking to get 3 linearly independent solutions. I'm expecting that now before I go into it. So this is a really important property of linear differential equations. So I'm going to note this is a key property. Okay? Okay, we're making a lot of progress here. We're making a lot of progress here. So let's go ahead and write down what our total solution looks like, right? What I'm going to do now is, yeah, I've written down x1 of t and x2 of t. I'm literally going to take my solutions x1 and x2, and I'm going to plug them in for each x1 and x2. And then we're going to keep going from there. So we'll start over here. So my total function x of t equals c1 e to the I omega t plus c2 e to the minus I omega t, where c1 and c2 are arbitrary constants. Whew. I still haven't addressed the elephant in the room here, that these solutions are complex in nature, right? These are complex numbers. And, you know, when I was writing out my differential equation, I mean, we're looking at a very real physical phenomenon with this spring here. And we know for a fact that we don't need complex numbers to express the position of my block, you know, at that's just a single number, a single regular real number. Why are complex numbers appearing, right? And so what I want us to kind of understand is that when I wrote out this differential equation here, right? Sure, in the back of my mind, right? I know that x at the end of the day, x as a function of time, should be outputting a real number. Absolutely. Position should just be some real number. However, this differential equation here, this is just some math expression. Nothing really restricts this equation from having a complex solution, right? Mathematically, right? Let me make that really clear. Math is just math. Math lets us do anything. So why not? Yeah, sure. Maybe this differential equation has a complex solution to it, right? And we know undeniably that the position of a physical block should be reflected with simply a real number. So let me make this very, very clear. So mathematically, what we're doing is we're choosing to allow. We're choosing to allow that my solution can potentially be complex. Why would we do that? Why would we choose to allow that my solution could be complex? I'll tell you why. Because we want this ansatz here. We want to use this extremely general ansatz here, x of t equals e to the alpha t. It makes our life 1,000 times easier to just think of this one ansatz. We could come up with another ansatz, right, that would satisfy this differential equation, and it wouldn't give us a complex answer either. Okay? We could absolutely do that. You want to know what that would be? If we proposed an ansatz in the form of sine of alpha t, and if we proposed an ansatz in the form of cosine of alpha t, right, we would end up getting the exact same thing. But this little package here of e to the alpha t is universal. It's always going to work in solving these differential equations for these oscillators of this form, right? It's always going to work. It's so nice. As long as we trade off, right? We're making a trade-off that, okay, my solution might not necessarily be real. I might get a complex answer. So what do we have to do? How do we resolve this? This is really easy to resolve. All that we do, right? All that we need to do is we simply take the real part of my complex solution. And that's it. Let's see if I can go ahead and like really fully expand out this this logic here to make this absolutely clear. Let me kind of see if we can diagram this thought process. At the beginning, in the conception of my problem, I knew that, yeah, this is going to have a real solution. That my block at every point in time is going to have a location that's simply defined by a real number. Now, in order to assist me, in solving the differential equation, I allowed the possibility that I could get imaginary solutions. I allowed it. And that allowed me to make a very, very convenient ansatz here, which I can use for many, many more problems, right? It's a very general ansatz. And then the cost of this, the cost of doing this, because I know, right? I know that my solution at the end of the day should be real. Great, I expanded my number system to assist me in this problem solving. And so now, but at the very end, sorry, this is getting kind of messy. At the very end, I need to convert back my solution by taking the real part of it, right? So I started with a real conception of the problem. I expand my number system out in order to assist me in solving the differential equation. That's great. And now I need to rein it back in. But we still just care about the real component of our answer because that is what's actually representing the position of my block. I hope that that diagram, that way of thinking makes sense because it's a really useful way. So truly in this sense, we can think of these complex numbers as a tool in helping me to solve a real world physical problem with a real solution. okay? Well, in that case, if we're feeling good about that, let's go ahead and do what I've been waiting for 50 minutes to finally use. I'm going to use Euler's formula, right? Ta-da! I can write, right, ei to the omega t. This is simply cosine omega t plus I sine omega t plus c2 cosine omega t plus I sine, oh, whoops, cosine of omega t plus I sine. And remember, this is minus omega t. Yes, you have cosine minus omega t in here, but by trig identities, cosine omega t and cosine minus omega t are equal. And of course, similarly, we can do something similar here and rewrite this as minus I sine omega t, just by trig identities. Oh, and let me just write this nicer. There we go, that looks nice. Okay? And so one thing that we might be tempted to do is, well, we just talked about this, right? Let's go ahead and just take the real part of this solution here. And so we can just ignore these I components and we're left with C1 cos omega t plus C2 cos omega t. And that's not exactly right. Why is that not exactly right? Well, remember, we expanded our complex number system, or we expanded to a complex number system in order to facilitate in solving this problem. If we expand it to the complex number system, C1 and C2 are arbitrary constants, right? So that means they can contain both a real and an imaginary part. So we have to be really careful. So in other words, I can write C1 as A plus BI times cos omega t plus I sine omega t. And next I can write C2 as C plus DI cos omega t minus I sine omega t. And we go through and we multiply this out. And what are we going to get? A cos omega t plus BI cos omega t plus AI sine omega t minus B sine omega t plus C cos omega t plus DI cos omega t minus CI sine omega t plus, right, careful here, plus times minus is minus, but then I times I is also a minus 1, so we get plus D sine omega t. All right? And what happens when we go through and we take the real part of this? Well, we can just go ahead and ignore all of the imaginary components, and we're going to be left with the following. A, let's combine like terms together. So this is A plus C times cosine omega t plus, and we're going to have D minus B sine omega t. And we can go ahead and call this a new set of constants, right? C1 and C2, right? And just to make us really comfortable, I made the C's like look a little bit different than these C's here, right? Because I'm redefining my constants now. So we're left with the following, right? And now we know that these constants C1 and C2, these are absolutely real as well, right? Because because A, B, C, and D, of course, in themselves are all real numbers. It's just we took B and multiplied it by I, and we took D and multiplied it by I. That's how we formed our complex multipliers. Numbers. Oh, so this feels great. Okay, now we have a real solution to this differential equation. X as a function of t equals C1 cosine omega t plus C2 sine omega t. Ta-da! Man, we worked really hard to get to this solution. But don't worry, right? I've been very careful in this video to kind of try and highlight as many properties as I can about differential equations. The reality is, this problem, takes almost an instant to solve, right? You can, once you practice, I mean, you look at these differential equations and you can solve them really, really quickly, right? Unfortunately, I hate to break it to you, we're not all the way done yet, right? Because we still haven't addressed the fact that C1, and by the way, I'm going to go back to just writing them as C1 and C2. I just wanted to distinguish earlier that these are different than the potentially complex constants. Okay, so anyways, but now I'm just going to write C1 and C2 back as normal C1s and C2s, and we know that these are real constants now. Okay? So C1 and C2 are still arbitrary. In other words, regardless of what I define C1 and C2 to be, again, because if I just take the derivative of cosine, or if I apply the differential operator on cosine omega t, this gives me 0, and 0 times any constant is still 0, so that checks out for any C1. And same thing with this sine omega t. If I plug it into my differential operator, it's going to spit out 0 at me too, and 0 times C2 is 0. So C1 and C2 are still arbitrary. They can be anything. So what's going on here? How can my solution have an infinite number of solutions? Well, the problem is we haven't yet applied initial conditions to the problem. So when we're in this form here, we call this form here, this is the general solution to my simple harmonic oscillator ODE. So we need to take this and we need to turn it into a particular solution. Correct? How do we specify a particular situation? Remember, F equals ma told us everything about the dynamics of the problem, right? It told us about really fundamentally the acceleration, the force, right? The force that this spring would put on this block at any position that the block's at. You know what we didn't define? We didn't define two things. First, we didn't define where the block is at t equals 0, right? Did I take this block at t equals 0 and put it here? Like I pushed the block in and then I let it go? Or maybe did I stretch the block out all the way over here, right? I stretched the block out, this is at t equals 0, and then I went and I released it, right? What was the initial position of my block? The other thing is, did I, for example, push the block, right, so that it could start moving? Maybe I took it here and then I also pushed it over to the left, right? I gave it a little nudge so it had some initial velocity, right? Maybe it had some initial velocity. right? Ooh, so that's really interesting. So I have two possibilities here. I can change the initial position of my block depending on whether I pull or press in on the spring and then release the block at t equals 0. And I can also control the initial velocity of my block depending if I, simply release it, in which case my initial velocity would be equal to 0, right? Or do I give it a little boost to give it some initial velocity? So that gives me two initial conditions, right? And so I'm going to call those initial conditions where I release the block x naught. So this is the initial position of my block. There we go. And I'm going to call my second initial condition v naught. This is the initial velocity of my block. And so let's go ahead and use these initial conditions to go from my arbitrary constants C1 and C2 and get a real, particular solution. We lock it down to just one solution. Okay? How do we do this? Well, this is really, really nice and easy then, right? We just have to apply the initial conditions. So my position at time t equals 0 is equal to x naught. Let's start with this. Cool. So x at t equals 0. And now I'm just going to plug in t equals 0 in this equation, right? So this is c1 cosine 0 plus c2 sine 0. Sine 0 is just 0. And this, of course, is going to equal, right? It's going to equal x naught, like we said. It's my initial position. Cosine 0, this is simply 1. And so we find that c1 equals x naught. Great, we've already got one of our constants written in terms of our initial position. That's fantastic. Next, let's go ahead and write out our initial velocity condition. So my velocity, which is the derivative of my position with respect to time, evaluated at t equals 0, this is simply going to be equal to v naught, like we said. All right, let's go ahead and take the derivative. What is dx dt? Well, this is very nice and easy. This is simply going to be minus c1. By the way, I'm just looking up here and I'm taking my derivative. Minus c1 omega sine omega t plus c2 omega cosine omega t. Nice and easy. And we already figured out that c1 is equal to x naught. So let me just place this guy. Cool. And again, let's go ahead and plug in that t equals 0. And so we have minus x naught omega sine 0 plus c2 omega cosine of 0. And this is going to be equal to, right, v naught. If this zeroes out and this here is equal to 1, then we're left with c2 equals v naught over omega. And finally, we can write out our final solution. X as a function of t equals x naught cosine omega t plus v naught over omega sine omega t. And this is a complete solution to our problem. Before I end the video, I just want to mention two things. The first is we can see that by defining k over m, by defining this as omega squared, we can see the physical significance of omega now, that this is the frequency, right? It dictates the frequency at which my cosine and sine waves oscillate in this equation. The second thing that I want to mention is it's very common to sometimes see, well, that's contradictory. It's very common to see x as a function of t written in a slightly different form for an oscillator as a cosine omega t plus phi. Notice how we still have two constants. This time a is your amplitude, though, and phi is your phase shift. We can see what's convenient about writing our equation in this form is that we've combined our cosine wave and our sine wave basically into a singular cosine. And you can also combine it likewise into a singular sine wave in a similar process. But I think this video has gone long enough. So really wanted to try and be as thorough as possible in my analysis of this differential equation to go over, a lot of really key properties that we can apply for any linear differential equation. I mean, look at all the stuff that we talked about and that we showed just from this very simple harmonic oscillator problem. I mean, we extracted so much information from this. So hopefully, even if you've never touched a differential equation before, after watching this video, you feel like you've picked up on a lot of different ideas between an ansatz and defining a differential operator and seeing what a linear ODE is, what a homogeneous ODE is, what the order of an ODE means, right? I really tried to fill this video up with as much information, about differential equations as possible so we can use these ideas going forward and just, for future problems, really solve these quickly. So, anyways, I hope you enjoyed this video. Thank you so much for watching.